Hey everyone, this will be the first video in my geometry series of my high school tutoring channel. So today we're going to be talking about the basics of geometry, such as proof. First of all, geometry is the study of shapes and figures, such as a square or a triangle, or even just a line. But we're not going to get deep into geometry today. We'll just be talking about the basics. I'm going to start off with a few definitions that everyone must know for geometry. An axiom is a rule that is accepted without proof. It's also called a postulate. And this, like it says, you don't need a proof. On the other hand, a theorem is a rule that can be proven and requires a proof. You've probably heard postulate and theorem before, but if not, these are the definitions. A corollary is a rule that's derived from a theorem. This is less common, and there are a few corollaries that we're going to be covering in our series. And then inductive reasoning is finding a pattern and deriving a rule from that pattern. When we get into reasoning, I'll show you an example. But the other type of reasoning is deductive reasoning. And for this, we need a conjecture. It's an assumption made to prove something. Inductive reasoning also creates a conjecture, but conjecture is usually used in deductive reasoning. A conjecture is not unproven because it's an assumption. And deductive reasoning, it uses properties and proven facts to verify if the conjecture is true. A proof is a logical argument to prove something true or to show that something is true. A locus is a set of points that satisfy a condition. In fact, the definition of a circle is the locus of points that are the same distance away from a center. For example, this is the center and this is the circle. Oh, that's a horrible circle. It's the locus of all the points that are, let's just say, 2 inches away from the center. And you might hear locus a lot in our circles unit. If two figures intersect, that means they share a set of points. Following this, an intersection is the locus of points that are shared by the figures. So if this triangle and this circle intersect, they intersect because they share points, and the intersection is the points that they share. Now that we've covered some basic definitions, I'm going to talk about some postulates and rules that we need for geometry. I'm going to borrow some from Euclid because Euclid, a famous mathematician, had laid out the postulates of geometry very clearly. His first one is a straight line segment can be drawn joining any 2 points. So if these are the 2 points, a straight line segment can be drawn between them. Any straight line segment can be extended indefinitely in a straight line. So if we were given the straight line segment with the points, you can extend it to form a line. Oops. These terms may not make any sense right now, but in our second video, I'll explain the essential definitions of geometry, which include line segments and lines. Given any straight line segment, a circle can be drawn having the segment as the radius and one endpoint as the center. As a drawing, we have the segment. Let's just say this endpoint is the center. It doesn't matter which one. We can draw a circle. Like this. It has the segment as the radius and the endpoint as the center. all right angles are congruent, it says that this angle is congruent to this angle. And as we'll talk about later, when angles are congruent, it means that they have the same measure. Last one, in a plane, given a line and a point not on it, there's exactly one line that passes through the point and never meets the first line. This is also called the parallel postulate, and you'll see why in a few lessons. So first, we're given the line and a point not on it. It says there is exactly one line that passes through the point, this point, and never meets the first line. Since it's a postulate, it does not have to be proved. So this is the postulates that Euclid laid out. But now we're going to be talking about something different, the rules of construction. In construction, we try to draw figures that are accurate. We prove theorems just using a compass and a ruler. Given a point, we can draw the lines that pass through the point. So given this, we can draw lines through it. Given 2 points, we can draw the line that passes through both points. Like I showed with the straight line segment and extending it, we can do that. Given a point, we can draw this circle centered at that point. Like I mentioned with the circle drawn with a segment as a radius and the endpoint as a center. Given a point and a segment, we can draw the circle centered at that point with the radius equal to the length of the segment. This is the exact same thing as Euclid's third postulate. Given 2 points, we can draw the circle through one point with the other point as the center. Like this. This is the center, and you can draw the circle. You may notice that a lot of these rules follow Euclid's postulates. And that's not surprising because, as I said, Euclid's postulates are the groundwork of all geometry. Moving on, we're going to talk about reasoning and how it's important to geometry. Reasoning and proof will be our main topics for this lesson. But first, we define a pattern. It's something that follows a specific rule. It can be objects like this. As you can see, it increases by 1/4 each time. This is a pattern because it follows the rule. But there's also number patterns like even 1, 2, 3, 4, 5 is a number pattern. 2, 4, 6, 8, 10 is a number pattern because you multiply by 2. And there are various types of patterns. Like I said, number pattern involves numbers, visual patterns involves objects. Inductive reasoning, as mentioned before, you take a pattern and write its rule. So the steps, first, you observe several examples and look for a pattern among them. Second, you make a general conjecture and modify it if needed. Step 3, verify the conjecture using logical reasoning. And this is where deductive reasoning comes in. But first, I'll give you an example of inductive reasoning. Let's say that we have to prove that when you multiply 4 to any number n, the result would always be even. This doesn't have to do with geometry, but it's just to prove using inductive reasoning. Now, in inductive reasoning, we'll find a pattern. So we set n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, and dot, dot, dot. As we can see, all of these are even. That is our conjecture. When you multiply 4 by a number n, it's always even. Now, I'll explain deductive reasoning before I use logical reasoning to verify. So if you prove a conjecture true, it is always going to be true. But to prove it false, you only need to prove it false once. It can be true every single time except for one certain time, and it'll still be false. A counterexample is the specific example that proves a conjecture false. Something, for an example of a counterexample, it could be that all circles have radius 2. And then I can draw a circle with radius 4. That's a counterexample. Now for deductive reasoning. Like I said, that involves logic. So law of detachment, if P, then Q, that's a statement. If that's true and P is true, then Q is true. This doesn't mean much now, but when we get into statements later this lesson, you will understand it. Law of syllogism, if P then Q is true, and if Q then R is true, then if P then R is true. So this one says, let's just say if I am 14 years old, then I am a teenager is true. And I am 14 years old, then I am a teenager. That Q is true. For an example of this, if I am 14 years old, then I am a teenager is true. And if I am a teenager, then I go to school is true. Then if I am 14 years old, I go to school. That's also true. These are the two laws. Now, to verify what we did back when we used inductive reasoning, we can use the mathematical laws that we know and prove this is true. Because when you multiply 4 and n, you get 4n. And you know that when you multiply 2 to any number, let's just say a, it'll always be even. And 4 is equal to 2 times 2, so it'll be 2 times 2n. And since you're multiplying 2 to a number, let's just say this is a, that means this will be even. So 4 times any number will always be even. This seems pretty obvious, but this is just an example of reasoning. Next, we're moving on to statements. A statement is a sentence that can be stated as true or false. For example, the sky is blue. That's either true or that's false. In this case, it's true. Truth value is whether a statement is true or false. Like I said, if we say the sky is blue, then this statement is true. The truth value is true. Equivalent statements are statements with the same truth value. So the sky is blue and the earth is round are both equivalent statements because they both are true. Statements could also be false, like the sky is purple or the earth is flat. Those both have the same truth value too, and those both are equivalent statements as well. A conjunction is statements that are connected with and. So an example of this would be the sky is blue and the earth is round. And for a conjunction to be true, both statements must be true. And in my example, both statements are true. A disjunction is a statement that is connected with or. So the sky is blue or the earth is round. And for a disjunction to be true, at least one statement must be true. So I can even say the sky is blue or the earth is flat, and it'll still be considered true. Negation is the opposite of a statement. So we say the sky is not blue, and that'll be the negation. The negation of a true statement is false, and vice versa. So when we say the sky is not blue, that would be a false statement, since the sky is blue is a true statement. A conditional statement consists of a hypothesis and a conclusion, an if-then format. As we saw in the previous slide, most statements used in deductive reasoning are if-then and conditional statements. The hypothesis is the condition and the conclusion is the result. An example would be, if it is raining, then I am wearing a jacket. Sorry for the messy handwriting, but this is an example of a conditional statement. The hypothesis is the condition. So if it is raining is the condition, and the conclusion is the result. Then I'm wearing a jacket. That's the result of it. A conditional statement is only false if a true hypothesis leads to a false conclusion. So for example, if the sky is blue, then or how about this? If the sky is blue, then the earth is flat. That would be a false conditional statement. But if we say if the earth is flat, then the sky is blue, that's still true. The converse of a statement is when we switch the hypothesis and the conclusion. So in the previous example, the converse would be, if I'm wearing a jacket, then it is raining. And it doesn't have to be equal to the statement, because it doesn't have to rain when I'm wearing a jacket. It could just be windy. It doesn't have to rain. So the converse of the previous statement is false. The inverse is when you negate both the hypothesis and the conclusion. So an example would be, if it is not raining, then I'm not wearing a jacket. This also doesn't have to be equivalent to the statement, because it is the same thing as the converse. If it is not raining, I can still be wearing a jacket if it's windy or if I just feel like it. It's always equivalent to the converse, like I mentioned before. The contrapositive is you negate and switch the hypothesis and conclusion. So it's basically negating the converse. An example of this would be, if I'm not wearing a jacket, it is not raining. And this is always equivalent to the statement, because if I'm not wearing a jacket, then it doesn't have to rain, it doesn't have to be windy, anything. But all we care about is it raining. And if I'm not wearing a jacket, it's not going to rain. A biconditional statement is when the statement is equivalent to the converse and the inverse. And many theorems we will look through this series will be biconditional. It's written as P if and only if Q. It can also be written as P if Q, IFF. Symbolic notation. So when we're writing statements, we can use symbols to denote other words instead of just writing them out. For example, as we've seen before, the hypothesis is usually written as P. And the other letters can be used as well, but P is the most common. And the conclusion is Q. Remember when we looked at the laws of deductive reasoning, we said if P, then Q. As with the hypothesis, other letters can be used as well. Then is usually written with an arrow. So it would be something like, if P, then Q. Not is with a tilde, or like this. That says it's the negation of the statement. And the conjunction would be written as a caret, or would be a downward caret, the disjunction. If and only if, would be written as an arrow that goes two sides. Truth tables. So truth tables are important because they show the truth value of statements. And I'll show a few examples of truth tables. A conditional statement like this: P, Q, if P, then Q. If P is true and Q is true, then the statement is true. If P is true and Q is false, then it's false. And I won't explain everything in the table, but it's important to know these. Like I said earlier, a conditional is only false if a true hypothesis leads to a false conclusion. The converse of a conditional would be the opposite. It's when a false hypothesis leads to a true conclusion. Inverse would be the same as converse, like I mentioned. And the contrapositive will be the same as conditional. The conjunction of two statements, however, it will be true only if the two statements are true. Disjunction, it'll only be false if both statements are false. I've mentioned these throughout the video, but this is for anyone who wants to pause and just copy these down, just to have them. A double conjunction, this is where it gets interesting. And I'm not going to explain it completely, but if you have three statements that are all conjunctions, then it can only be true if all three statements are true. This matches with what we said about a conjunction. It can only be true if the two statements are true. Now, if all three are true, it can be true. It's a conjunction and disjunction. This one, it is much more complicated, and I'm not going to explain it fully, but P and Q must be true for this part to be true. And P and Q or R must be true. And it's extremely confusing. So I'm not going to explain it, but you can copy this down if you want to. Now we'll talk about the properties of equality, which are really important in proving statements. The algebraic properties of equality. So given A, B, and C are real numbers, this is an important part, by the way, because if they're not real numbers, then none of these properties work. So if they are real numbers, we have if A is equal to B, then A plus C is equal to B plus C. This seems pretty obvious, something like in pre-algebra. If A is equal to B, then A minus C is equal to B minus C. If A is equal to B, then AC is equal to BC. If A is equal to B and C is not equal to 0, then A divided by C is equal to B divided by C. We have this extra condition because if C is equal to 0, then you're dividing by 0, which does not happen to be a real number. If A is equal to B, then A can be substituted for B in any equation. So what we're trying to say is that if we have A plus 5 is equal to 7, and we also know that A is equal to B, then we can derive that B plus 5 is equal to 7. Some other properties that are not algebraic are the distributive property. A times B plus C is equal to AB plus AC. And notice how we write A, B, and C are real numbers again. For any real number A is equal to A. Well, that's kind of obvious. For any real numbers A and B, if A is equal to B, then B is equal to A. For any real numbers A, B, and C, if A is equal to B and B is equal to C, then A is equal to C. These three last ones seem extremely obvious, but they're extremely useful in geometry. Notice the last one. It looks a lot like the law of syllogism. And that's because it's true not only for statements, but also for real numbers. Proofs. So this is what we've all been talking about, because proofs are the key to geometry. A proof, like mentioned before, is a logical argument that shows a statement is true. The hypothesis is given and the conclusion is proved. And that makes sense because the condition is given, that's what you're given, and the result is what you're trying to prove. There are different types of proof, and one of them is the two-column proof, and it has numbered statements and corresponding reasons in logical order, like this. So we have our first statement here, and then the reason for that. And the reason is usually some theorem or postulate that we have. And then we have the second one, our statement, and then the reason, and so on and so forth. Paragraph proof involves a paragraph, as said by the title, and that's just keeping on writing and giving your reasoning along with your statements. A flow proof uses arrows, and it's something like this is statement, and this is the reason, and then you go to this one, statement, reason, And usually what you prove, when you're done with it, you write it in a box and then your reason down here. Proof by contradiction, it involves using a counterexample to prove that something is false. So a proof doesn't have to be something that a statement is true. It can be that a statement is false. And this is an example of it. So we can say that since 2 is not greater than 3, it means that all real numbers don't have to be greater than 3. And that's it for today's class. Thank you.